So welcome back to the series of engineering mathematics, and today is lecture number 5 of differential equations actually. Okay, so we have started differential equations, of course ordinary differential equations, and we started looking at the first order equations in the last lecture. Okay, so just a second, I think there is an issue. Okay, fine. So we have started with the first order differential equations. Until the last lecture we have seen the linear equations and of course the exact equations. Okay, so the exact equations, integrating factors, and then converting non-exact equations to exact equations by multiplication of integrating factors actually. Okay, also we have seen certain set of rules to figure out what is the how to figure out actually the integrating factors. Okay, so let's see. But before I straight away go to the topics, I would like to give a quick update on the Telegram channel, and any update for the content coming out will be posted on this particular channel. Okay, and also this is the Telegram channel for our group actually, so we can if some of you need any information or any guidance kind of thing, you can just enroll it, you can just join the Telegram channel actually, so that you'll be getting in touch with 1500 of your fellows who will be on the same lines, okay, of GATE examination. So let's see. I also strongly advise you to install Unity so that you can have the track of all your content at one particular place actually. So when you type the doubts, you can type exclamation doubts, or when you type a note point, you can type exclamation note, and you can type the points actually. Okay, so that they all get stored at a particular place in general. Okay, so in the last lecture we were talking about exact equations. We were talking about the exact equations. Okay, and in the exact equations we have seen, like normally if you have m of x comma y dx plus n of x comma y dy is equal to 0, then we have seen this is some differentiation of an exact derivative of a function. Okay, so this tells you there is a function for which the exact derivative of that function is given by this. Okay, and the mathematical condition which checks up is actually dou m by dou y is equal to dou n by dou x. So this is mathematical check for exactness. So there is a mathematical check for exactness actually. Okay, so mathematical check for the exactness. Okay, homework first solve. I'll solve, yeah, wait. First of all, let's have a view, okay, what we have learned actually. Then we have figured out something like integrating factors, IF. So if you take any non-exact equation and if you multiply this with integrating factor on both sides, then this turns out to be an exact equation. Okay, and we have seen the way to write the solutions for the exact equations. Okay, then let's see, we have also talked a bit about linear equations of first order. Linear equations of first order actually here. Okay, and I have shown you linear equations of first order, of course, and the general form is of the form dy by dx plus some function in terms of x is equal to some function in terms of x actually. Okay, so p comma q are functions of x alone, functions of x alone, and we have seen the integrating factor in this case is equal to e power integral p dx is what you get. Okay, then we have solved this question. Of course I have shown you the solution. The solution to this is y into e power integral p dx, or basically y into if is equal to integral of q into if dx plus constant. Okay, so these are the things which you have seen. So in today's class basically we'll work on equations reducible to linear equations. So when there are certain nonlinear equations, then we can convert them into linear equations, and the most important part is applications of first order equations is what we are going to look in today's class, of course. Okay, so let's see. So before this, let's go for the homework since some of you are much excited. So what is the answer for this question? I've asked you to enter up to 3 decimal places, so 30 seconds. If you have solved, then enter the answer. This is the homework question what I've given you. Okay, so come on, solve this. .52. Okay, so you have solved this, that's why you're much excited. Okay, let's see. But yeah, but it's good always to answer the question. Okay, so well, if some of you have solved, then you might have entered the answer. Let's try to solve this question. Okay, so yesterday's homework. So given dy by dx is equal to 2x minus y So this tells you dy by dx plus y is equal to 2x actually. Okay, so just if you shift this y to the left hand side, okay, 0.88, okay, even I don't know the answer, to be frank. Let us solve. Okay, then we can write 1 here, of course. So when you write a 1 here, it's of Leibniz linear form. This is of Leibniz linear form actually here. Okay, then what about integrating factor? E power integral p dx, so which is e power x actually. So that's the integrating factor, right? Because I have shown you, if this function, which is of course in this case it's a constant, so if that can be written as 1 into x power 0, of course. Okay, so it turns out to be e power x actually. So therefore solution is y into this integrating factor is equal to integral 2x into e power x dx plus constant. And we know the technique for writing this integration. Y into e power x is equal to 2 if you take common, first function integration of second minus derivative of first into integration of second, and that's all, plus constant. So what we can do is, maybe we can cancel one e power x and write a e power minus x, of course. Okay, so I can do that, right? I can cancel e power x in each and every term, so that there comes e power minus x onto the last term. So what's the solution? Finally we have y is equal to, let us write it here, let us conserve the space. So y is equal to 2 times of x minus 1 plus constant times of e power minus x. So this is the solution that you have here, right? So y is equal to 2 times of x minus 1 plus constant times of e power minus x is what you have. Okay, so let's solve this. For getting the value of the constant, see, they have given you one condition. Let's say y of 0 is equal to 1. Okay, so given y of 0 is equal to 1. So what does this tell you? At x is equal to 0, y value is equal to 1, obviously, correct? So that's what y of 0 is equal to 1 tells you. So if you put x equal to 0 and y equal to 1 simultaneously in this equation, let's see what you will get. So this tells you 1 is equal to, so y value is 1, 2 into, if you place x is equal to 0, this is minus 2, plus c into, if you put x is equal to 0, e power minus 0 is just 1, that's all. Okay, so this tells you c is equal to 3 actually. So the value of the constant is 3. So once you know the value of the constant, you can tell the solution. Therefore y is equal to 2 times of x minus 1 plus 3 into e power minus x. This is the final solution which you all got, yes or no? So those who told the answer, so let's confirm, is this the final solution? What you got? The value of the constant is 3, right? Come on, quickly confirm it. Did you all get this solution? Okay, now they are asking you value of y at x equal to ln 2. Okay, so at x is equal to ln 2. At x is equal to ln 2. So this is 2 times of ln 2 minus 1 plus 3 into e power minus ln 2. So e power minus ln 2 gives you 1 by 2. That's it. Okay, so let us compute this value, because e power minus ln 2 can be written as e power ln 2 power minus 1, so which is 1 by 2, of course. Okay, so that's why this e power ln 2 is 1 by 2. So 1.5, and this simplification we have to do a bit clear. So that's it, right? Yeah, I think things are clear. So let's compute the value. Ln 2 minus 1, ln 2 minus 1, so this value into 2 actually, so minus 0.613 plus 1.5, 0.886, yeah, 2.886 is the actual answer. So 3 decimals, 0.886, yeah, that could be good enough. So 0.886, because I have asked you to 3 decimals. Okay, so let's enter the answer. 0.886. Come on, shake it down. Okay, poll is not working. Students participated 0, it has shown, but 0.52 is not the answer. Shravan, 0.88, yeah, I think you're correct. Okay, so 0.886 is the actual answer. Fine, so 0.886 is the actual answer in this case. Okay, is this clear to each and everyone? Your answer is always wrong. No, see, don't feel that. Whenever you commit some mistakes, you should always learn from your mistake. Okay, fine. It's not like something which we did not discuss in the class or something which you cannot think. Okay, it's an easy question, but the idea here is when you are making substitutions, it slightly there is a high chance of doing calculation mistakes. And I think definitely you might have got this solution, okay? But when you have substituted ln 2, the answer might have changed. So please be careful with these kind of, calculations a bit, okay? Yeah. Come on, guys, confirm. Good evening, Rambabu. Just confirm the answer. Is this clear to each and everyone? If this is clear, we'll move on to the today's topic. Okay. So fine. Let's look at today's topic then. Equations reducible to linear form. So basically we know the techniques to solve linear equations, but many times it happens there are non-linear equations, okay? Not many times, 99% of the times it happens the equation is non-linear, okay, in real systems, okay, in the real world. But few times we can convert the non-linear systems into linear systems by making certain substitution actually, okay? So let's see what are the substitutions we can make. So the first thing is Bernoulli's equation. Bernoulli's equation. So this is not the one what you see in your generally the fluid mechanics. It is something different. So dy by dx plus p times y is equal to q times y power n, okay, in bracket n greater than 1, of course, okay. To be more precise, n is not equal to 1, okay. So n is not equal to 1 actually here in this. So fluid mechanics is a subject, okay, don't worry right now, I'm not going to teach that. So this is n is equal to 1, of course, sorry, n not equal to 1 actually. Fine. So this is n not equal to 1. Now let's see. This is clearly a non-linear equation, right? Because if n is greater than 1, then ultimately this degree is more than 1. So ultimately it is non-linear, okay? But by making certain substitutions, we can convert this non-linear equation into linear equation. Let's check it up. If you divide with y power n on both the sides of the equation, you have y power minus n dy by dx plus p into y power 1 minus n is equal to q actually, okay. So that's the equation you have. Yes, because if you divide with y power n on both sides, there comes 1 by y power n, which gives you y power minus n actually here, okay. Okay, you're from sorry, mechanical branch, okay. Then in fluid mechanics we have the Bernoulli's equation, right? You remember dp by rho plus v dv plus g times dz is equal to constant. You might have seen this differential equation, or 0. This is equal to 0, of course. It's in differential form. This is the differential equation where you have different terms like pressure, density, velocity, gravity, okay. Then change in elevation, of course. We can derive this equation. If you apply this Euler's equation along a streamline, you can end up with this equation, okay. But anyway, this is a different story which we'll see later. So right now, if you have y power minus n into dy by dx plus p into y power 1 minus n is equal to q, okay. So that's what you have. Then if you make this substitution, let y power 1 minus n is equal to, say, some variable, let's say t, okay, some variable, whatever. So this is, let's say if I take this as t, this ultimately gives me 1 minus n into y power minus n into dy by dt is equal to 1 actually, okay. Or you can write this as 1 minus n into y power minus 1. If you differentiate with respect to x on both sides, dy by dx is equal to dt by dx. I can write it, okay. I have taken this y power 1 minus n as t, and I have substituted, basically I have differentiated with respect to x on both sides. So if I differentiate with respect to x on both sides, y power 1 minus n, this is some power, so 1 minus n will come here, and y power, see, if you differentiate this with respect to x, of course, okay, d by dx of this guy, it tells you 1 minus n into y power 1 minus n minus 1 dy by dx is equal to, so this is what the derivative, of course, okay. Then you can see this 1 and 1 gets cancelled. You have 1 minus n y power minus n dy by dx actually, okay. So this complete expression is what you'll get if you differentiate this with respect to x actually, and you have this value here 1 minus n y power minus n dy by dx, and of course dt by dx, because you are differentiating with respect to x actually, okay. Then let's see if this is dt by dx. So ultimately, therefore, if you call this guy as 1, equation 1, maybe I'll use different color. So this is equation 1. Therefore, equation 1 implies, look, y power minus n into dy by dx. This can be written as 1 by 1 minus n times dt by dx actually, okay. Plus, because ultimately this term is here, so this 1 minus n, if you send it to the denominator on the right hand side, 1 by 1 minus n into dt by dx plus p times then y power 1 minus n is taken as t, and on the right hand side there is no y, so this is q of course. Okay, now if you observe this equation little carefully here, this equation tells you dt by dx plus this 1 minus n will get multiplied to this p times t is equal to 1 minus n times of q actually. Okay, now n is just some number, okay, like 2, 3, 4, whatever, it is some number. Now if p is function of x alone, 1 minus n into p is also a purely function of x. Similarly 1 minus n into q is also function of x of course. Okay, so you can write it as this is function of x alone. Okay, even this of course. Now this equation can be written as plus, maybe let's call this as some function which is only of function p, what can we denote, p1, let's say p1 times t is equal to q1, where p1 and q1 are only functions of x. So this is again a linear form. Okay, but here the independent variable is t, independent variable is x, dependent variable is t. So once you solve this equation, you'll get answer in terms of x and t. So you can put back t as y power 1 minus n. So you'll have the answer again in terms of x and y. So using a concept of linear equation, you can actually solve this nonlinear equation. Clear to all of you? Did you all understand? This is Leibniz linear if form. Leibniz linear form. So for this, we know the technique, e power integral p1 dx is the integrating factor. If you multiply, and you'll get the solution of course. Okay, the solution will be in terms of t and x, but if you replace t as y power 1 minus n back into the solution, you'll have the solution in terms of x and y actually. Clear to all of you? Please type it in the chat box. So Pavan, Rambabu, Satya, Anjan, and many others of course. So please type it in the chat box. Is this clear to all of you till this point? Did you all understand how we can actually solve this equation? Yes? Now I'll give you a poll, maybe you can try something. Single choice, I'll give you 4 minutes to solve this. Or 3.5 minutes could be good enough, I think. Single choice, start. By the time this poll ends, I'll stop that. Come on, do this. This is the differential equation. I hope you can see the text is maybe a bit dull. So if you just want me to brighten it, e power x times x plus 1 dx plus y into e power y minus x e power x dy is equal to 0. That's the equation. Okay, and y of 0 is equal to 0. So you have the options actually. It's actually a question from the test series. It's a nice question of differential equations. So I thought of solving this question once again here. Come on, do this. This is the equation, okay, and this is the solution. Just a second, I'll have water. Come on, fast. Clearly it's a nonlinear equation, okay, you can see, because there is y into e power y, it's nonlinear equation but of first order. Okay, solve this. D, maybe, I don't know, I'm not sure, I have to solve this. Okay, but it's a nice question in the test series actually. Okay? One of the nice question the test series, so sort of putting it. Last 1 minute. Last 30 seconds. Come on, type, think faster. C. Okay, all of you want to solve C. Go for C. 2y e power y plus x minus x square is equal to 0. Okay, maybe. Let's see whether it's C or not. Okay, 8, 5, 4, 3, 2, 1. If some of you want to enter C. Okay, all of you want to say it's C. Good. So I think my example of that hostel dosa, my example got worked out. Okay, all of you are showing unity. But let's see what the answer is. Okay. Solution. Given e power x into x plus 1 dx plus y e power y minus x e power x dy is equal to 0. Okay, so that's the equation. Maybe one way I can solve this question is, if you observe this term little carefully, e power x into x plus 1, that's actually the derivative of this x into e power x. Correct? That's what I have given. Obviously, you can see this e power x into x plus 1 dx is actually the derivative of this x into e power x. So what I'm going to do is dy actually. Okay, so if I do this, then I can have e power x times of x plus 1 dx by dy, then minus x into e power x is equal to, maybe you can take this to the other side, we have minus y times e power y, of course. Okay, so that's the question that I can have. See, the only thing is I have divided this with dy, so that dy here gets cancelled and you have dy here. So this function as it is, minus x into e power x, and this y into e power y, I have put it on the other side. Okay, then let's see, let x into e power x is equal to t, maybe you call that to be t, so that, because here if you have some function, here you have exactly the same function, of course. Okay, so let's see, let x into e power x is equal to t. So if you differentiate both sides with respect to y, we have first function into derivative of second function e power x into this x is there, so dx by dy, plus second function into derivative of the first function, which is dx by dy, is equal to dt by dy actually here. So this can be written as, if you take dx by dy common, you have x plus 1 times e power x into dx by dy is equal to dt by dy, of course. Okay, so that's what I can write. Correct? How do I know? Because we figured out something like, if this term, if you see, this term is something like the derivative of this function x into e power x. Okay, so this can be replaced with dt by dy. So if you replace this, let's see what happens. Therefore, given dE is this complete first term can be replaced with dt by dy. So dt by dy minus, you have minus t, of course. Okay, so you can write this as plus minus 1 into t is equal to some function of y minus y into e power y actually. So clearly this is of the Leibniz linear form actually. Okay, so this is Leibniz linear form, because you can easily figure out this derivative is dt by dy, which means independent variable is y, dependent variable is t. So dependent is t, so you have some function in terms of y into t, and this is purely a function of y alone. Okay, so this is in Leibniz linear form, because in this particular differential, this y is the independent and t is the dependent. Is this clear to all of you till this point? If this is clear, then the job is almost 80% done. But please confirm. Just by making this simple substitution as t, within these two steps, you can identify the given equation can be converted to Leibniz linear form. Is this clear to each and everyone? Come on, type it in the chat box. Every one of you. Yeah? Okay? A bit faster. Just confirm it. A bit quick. Okay? Yep. So let's solve this question then. let's go for the integrating factor. Therefore, IF is equal to e power integral minus 1 dy this time. Okay, because this is the independent variable, y is the independent variable actually. So e power minus y is what I get. So therefore, solution is t into integrating factor e power minus y is equal to integral this function minus y times e power y into the integrating factor e power minus y dy plus constant. That's what you get. Okay, so then you can cancel up these two things. It turns out to be t into e power minus y is equal to integration of minus y is minus y square by 2 plus constant. So what is t? Let us, because the actual equation is in terms of x and y, so the final solution should also be in terms of x and y before you substitute the boundary conditions. Okay, so t is actually x into e power x. Let's get it back. So x into e power x into e power minus y is equal to minus y square by 2 plus constant. Okay, so this tells you x into e power x minus y is equal to minus y square by 2 plus or plus y square by 2, maybe you can put it this side, plus y square by 2 is equal to constant actually. Okay, so this is constant, right? So this is constant value. So this is constant. Okay, now since this is the actual solution, the final solution of the equation, but it's a general solution. Okay, if that's a general solution, then to get this constant c, we should apply one boundary condition. So that boundary condition value is given, of course. So if you apply y of 0 is equal to 0, let's apply that. Given y of 0 is equal to 0, this tells you at x is equal to 0, y is also going to be 0 actually. So if you substitute these guys here, x is equal to 0, so 0 into e power 0 minus 0 plus 0 square by 2 is equal to c. So ultimately constant value is 0 in this case. If you take the boundary condition, y of 0 is equal to 0 actually, because clearly 0 into 1, e power 0 is 1, so 0 plus 0 actually, so constant is 0. Therefore solution is, if you put the c to be 0, we have, if you multiply with 2x e power x minus y plus y square is equal to 0. That's all. So that's the solution, particular solution for this particular given boundary condition. Okay, so 2x e power x minus y plus y square is equal to 0. Let's check if this is somewhere. 2x e power x minus y, 2x e power x minus y plus y square. So option B is the correct answer. Option B is the correct answer. Okay, not C. Unity should be correct. Okay, not like 100 people stand on the same wrong side, but at least I think those are example what I told the other day worked out. Correct. So anyway, this is the correct option for this question. Okay, so 2x e power x minus y plus y square is equal to 0, of course. Clear? Any doubts in this, or is it fine? Just type it in the chat box. Is this fine to all of you? Can you all recognize this solution is correct? Okay, I think I did not skip anything. Plus minus minus, so then minus 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 plus minus. Yeah, I think it's correct. Two. Any doubts in this question, or it's fine? All of you. This is actually a question which was asked in test series this year. I have set this question, of course. So it's really nice thing. This time Unity are not working because it's copy all students of one student. Okay, but anyway, this is the question. Okay, to solve this hardly 3.5 minutes is sufficient. Okay, because if this point gets in your mind, 30 seconds, 1 minute, then this is completely hardly 1.5 minutes, so 2.5 minutes, 30 seconds, 3 minutes. Okay, but I have given you 30 seconds excess. So kind of me, right? So let's give one more question. Solve this. dy by dx plus 7x square y is equal to 0. This q function is 0. Okay, if y of 0 equal to 3 by 7, then the value of y of 1 is dash, round off to 3 decimals. Come on, do this. Fellow is not taking poll. Why? Oh, it has taken. Good. Students participated: Shravan Singh, Ashwini Kumar Biswal. Okay, but then it's not showing. Why? Hello, is a type, and 150 is good enough. Cut. Come on, quick. Don't do calculation mistakes, okay? Do carefully. Three by 7, but y of 0 is 3 by 7 na, already. So y of 1 is also 3 by 7. I don't think so, because dy by dx is non-zero actually at x equal to 1, right? Dy by dx not 0, correct? So the time is going up fast. Roshan, Shravan, Sujay, this time chat box is silent. Back of the previous question. Okay, good. So it got stopped. Now honestly tell me, I'll do a procedure. How many of you have done that? Dy by dx plus 7x square y is equal to 0. So integrating factor is equal to e power integral 7x square dx, so which is e power 7x cubed by 3. You have done this? Yes? How many of you have done this calculation of integrating factor? Please type it in the chat box. How many of you have done this calculation of integration factor? It's okay. I know some of you might have done, definitely. Is there someone who have done this calculation of integration factor here? No. Don't want to admit. Okay, fine. So you have done it, right? Yeah, okay. So this is one way, of course, which you can solve. So this implies solution is y into integrating factor e power 7x cubed by 3 is equal to constant. So this is the solution. Okay, if you calculate it in this way. So this is the solution, of course, because ultimately the right hand side is 0. So integral 0 into integrating factor, because the right hand side is 0, so q function is 0. So integration of 0 into something is 0 plus constant, so you have a constant. That's the solution. Or you would have also done it as, sorry, you might have also done this question as dy by dx plus 7x square y is equal to 0. So this tells you dy by dx is equal to minus 7x square y actually. So if you bring this x square y 1 by y to the left hand side, minus 7x square dx, it's a variable separable form directly. Okay, of course you can do it in the linear equation form, either like this or you might have done it like this. Okay, so in any way you might have got the solution. So if you integrate this guy, it tells you ln y is equal to minus 7x cubed by 3 plus constant, of course. Okay, so ln y is equal to minus 7x cubed by 3 plus constant actually. So this can be written as y is equal to e power minus 7x cubed by 3 plus into constant actually. So how you can write this as constant is, look, I'll tell you. Normally you can have plus constant, okay, because this c is on the right hand side. So this can be written as e power minus 7x cubed by 3, this term plus constant. Okay, but this term plus c can be written as into e power constant, correct? Because there is plus c here, so that plus c can be broken up into product of two exponential terms. And for arbitrary constant c, this e power c is also one arbitrary constant. Okay, so that's what you can replace it with c actually. Got it? So either you do it this variable separable form or you do it by Leibniz form, you should get the same solution. Of course, this is, both are same actually. If you throw this e power 7x cubed by 3 to the other side, you will get e power c into e power minus 7x cubed by 3. Okay, so both the solutions are same. It is variable separable form and that's Leibniz form. Now let's see, they have given you one boundary condition to get this value, y of 0 equal to 3 by 7. So let's see, y of 0 is equal to 3 by 7 actually. Okay, so y of 0 is equal to 3 by 7. So if you put x equal to 0, y value is 3 by 7. Okay, let's substitute both in this simultaneously. Y is 3 by 7 when if you put x equal to 0, this is e power 0 1, so this is the value of constant. Okay, so what is the solution finally? Y is equal to 3 by 7 times of exponential minus 7 y equal to 3 by 7 times exponential of minus 7 x cube by 3 actually here. Okay, so when you put x equal to 1 on both sides, because that's the location where you are interested, so if you put at x equal to 1 on both sides, anyhow this is a constant, at x is equal to 1, so this implies y of 1 is equal to, so when you put x equal to 1, this is 3 by 7 times e power minus 7 by 3, e power minus 7 by 3. So you have to calculate this value and enter up to 3 decimals. Okay, so you can enter up to 3 decimals. Let's check the value. 3 by 7 into exponential of minus 7 by 3. The reason why many of you are getting different answers is calculation of this minus 7 by 3 is wrong in your case. Okay, so let's check it out. Minus 7 by 3. First you calculate minus 7 by 3 and click equal to. Only after clicking equal to sign you should click exponential, otherwise the answer would be wrong. Okay, now if you click exponential, this is e power minus 7 by 3 into 3 by 7. So into 3 by 7 actually. So 0.041. 0.0415. So you can round off to 2 actually. Okay, so 0.042 is the actual answer. Clear? So what some of you might have done is, when you are trying to calculate this value minus 7 by 3, look, minus 7 by 3 exponentially might have typed. Okay, so you can see clearly it is minus 7 by e power 3. Okay, it is minus 7 by e power 3, not e power minus 7 by 3. Clear? You can clearly check this, and if you click equality minus 0.348, that's the value, which is something wrong. Okay, so when you are doing exponential functions, trigonometric functions, or anything in this calculator, first of all, if you want 7 by 3 with a minus sign, minus 7 by 3, you click equal to, then you click on e power x. So e power x is applied to minus 7 by 3. Okay, so into 3 by 7 of course. So 0.041 is what you have. Okay, 0.041 is the actual answer, and 1.716, all these cases would have come because of doing some mistake actually. Okay, so 0.042 is the actual answer in this case. But these are the two techniques in which you can solve the question. कैल्सी ने धोखा दे दिया, कैल्सी धोखा नहीं देते हैं. Okay, we ourselves fall in the trap. When we are solving gate questions, please use virtual calculator. Okay, I know the impact of that. Okay, it's almost like twice I missed all India rank 1 because of that. Okay, so please use using virtual calculator and do it. Fine. So this is one case where you can actually convert this into differential form. So this is Leibniz linear equation. So on solving, you know, t is equal to some function of x. T can be replaced with y power 1 minus n. This gives you y is some function of x actually. Okay, that's what you have. Fine, that's what I have done basically to solve this. Okay, then one more thing, I have put a constraint n is not equal to 1. Okay, what is the case if n equal to 1? What is the problem you have? So here in this case you can see this 1 by 1 minus n is coming in the denominator. Okay, if 1 by 1 minus n comes in the denominator, and if you put exactly n equal to 1, this term becomes 1 by 0, and division with 0 is not defined. Okay, so for this to be non-zero and for this to be defined, this n value should not be equal to 1. Okay, now if n is equal to 1 for example, then how you are going to solve the question? Okay, that's the, obviously I have given the constraint n is not equal to 1, but it can be possible that n can also be equal to 1 sometimes. Okay, so if n is equal to 1, then how you are going to solve this equation? Let's check. For n is equal to 1, dy by dx plus p into y is equal to q times of y actually. Okay, because this n value is 1, so it is just qy, and this can be written as dy by dx is equal to q minus p times y of course. So 1 by y dy is equal to q minus p dx, and clearly p and q are both are functions of x, so the right hand side is function of x. It's a variable separable form. You can just integrate and get the answer. Okay, so if you integrate these two guys, this finally gives you a solution in terms of x, and you have vast knowledge of integration, integrating single variable functions. You have seen in single variable calculus, so it's how it can be done. It's simple variable separable form for n is equal to 1 actually. Okay, so this is one case where you can convert this into linear equations. The second case is the equations of the form of the form f dash of y into dy by dx plus p into f of y is equal to some function, say q, okay, where p comma q are functions of x alone again. So where p comma q are functions of x alone, okay. So these are functions of x alone, of course, and clearly you can mark it up. So in such case, for f of y is equal to, say, some t like this, okay. So this tells you f dash of y into dy by dx, the same thing what we have done in the example. So this is dt by dx actually. So this tells you, if you replace this quantity with dt by dx plus p into t is equal to q, that's it, okay. So it is again Leibniz linear form. Leibniz linear form actually, okay. So this is Leibniz linear form, and once you have this sorry, hi Shubham. So look here, so this is Leibniz linear form actually here, and once you know this, then ultimately on solving you know how to solve these equations. So on solving, this t is going to be some function of x, so this tells you f of y is equal to some function of, you know, basically something in terms of x actually, okay. So basically if you simplify a bit, you'll get y is equal to some function of x on replacing t is equal to f of y actually here, okay. So you'll get the final solution in terms of y and x, of course, if y and x are the variables involved. So these are two cases in general where you can convert the you know, the differential equation which is of first order nonlinear into first order linear equation, okay. And many times in gate examination they've asked you questions like this. They have given this equation, and below, for which substitutions given below, the value, or basically this equation gets converted to linear form is what the question is, and they'll give you this substitution in one of the answers, okay. Y power 1 minus n equal to t, y power minus n equal to t, they'll give you 4 options like this, but this taking y power 1 minus n equal to t converts this nonlinear to linear form actually, okay. So please make a note of these things. Then let's look at applications of first order equations, okay. So you have plenty of applications, like day in and day out you get first order differential equations every almost physical problems. So let's talk about some 2-3 frequent examples which we encounter, okay. So first thing is Newton's law of cooling, which many of you might have seen, okay. Newton's law of cooling. So it can be used for heating also, but initially Newton did the experiments for cooling, so that's why the law is named like that. But of course it can be used for heating as well, okay, no issue. So let's see, if you take a body, for example, if this body is having a temperature T at a instant, let's say at some time T, and the surrounding temperature is infinity, okay. So let's say if the surrounding is very big, let's say for example if I place one small hot lead ball in this big room, then ultimately heat escapes from this ball, okay. So this is T infinity, then ultimately, you know, if this is hot sorry, so if T is greater than T infinity, then ultimately heat flows outside this body, because by default heat flows from low temperature to, heat flows by default from high temperature to low temperature, so we have heat flowing. Now ultimately the area of the body is fixed because it's a solid body, let's say, okay. Then of course right now I'm taking solid because I want to simplify the expression. Now if you take this body which has some constant surface area, in such case what can be done is, this heat depends, the heat flow depends upon the difference between these two temperatures, correct? Can you all understand this? The heat flow from this body to the surroundings depends upon the temperature difference, because if higher the temperature difference, faster will be the heat transfer. Yes, let's say for example, you know, you're cooking some food in your kitchen, okay, and let's say once it is heated for sufficient amount of time, if you just touch it, immediately you'll feel hotness, okay. But let's say if something is at low temperature, okay, just slightly 2-3 degrees more than the room temperature, then if you keep your finger there, ultimately it takes some time, considerably more time, for your finger to get heated up, okay, because the amount of heat that gets transferred takes time, and it is time dependent, of course, and it depends on the difference between T and T infinity actually, okay. Then can someone understand something, that for a body, I'll just Do you all know law of conservation of energy? Energy can never be created nor be destroyed. So let's say if things are changing like this, energy flowing in to the body minus energy flowing out of the body is equal to rate of change of energy of the body actually. Okay, this is what you write. And of course, if you make simplifications, right now I'm not going into the physics of the heat transfer, what's going on, but you can figure out one thing finally on using proper physical analysis for the system. Okay, so right now I'm not doing all these things. Maybe it would, if this is a mechanical engineering class, or if it's a, let's say, some heat transfer class, I would have shown the derivation. But right now just try to understand something, that dt by dt small t, okay, where t is the time, this is actually proportional to t minus t infinity, but with a minus sign, of course. Okay, so this is with a minus sign, or in general many times people don't put this minus sign because the constant value can be calculated accordingly. So but of course why I have put a minus sign is, this can be written as dt by dt is equal to minus k times of t minus t infinity, where k is proportionality constant, of course. K is proportionality constant, and obviously k is positive. Okay, if k is positive, only then you should put this minus sign. Okay, if k is negative, then ultimately you need not put this minus sign, of course. So this is the differential equation. Okay, and of course this k depends upon a lot of stuff like heat transfer coefficient, area, all. There is some physics which governs it. Right now we are not looking into that, but this is the thing. Now why I have put a minus sign, because if this body is hot, T is greater than T infinity, then obviously heat flows outside the body. If heat is flown outside the body, then what happens to the temperature of the body with time? It increases or decreases? If heat is flowing out of the body, if T is greater than T infinity, then heat flows out of the body. If the body is losing heat, what happens to the temperature of the body in this case? With time, as time increases, what happens to the temperature of the body? It increases or decreases? Come on, quick, a bit fast. Will it increase or decrease? Decays. Okay, so if that temperature decreases with time, so if dt, I mean d small t, change in time, is positive, ultimately change in temperature is negative. Okay, so this ratio is always having a negative impact. If this increases, this decreases when t is greater than t infinity. Okay, so that's why this is for cooling. For cooling. Okay, so this is for cooling actually here. And on k has dimensions. K is also a dimensional constant which has 1 by second, of course, like you can see 1 by h, whatever the terms you consider. So this k has the dimensions 1 by h, because the equation should be dimensionally matched on both the sides. Okay, then let's see. I'll ask you a question now. Try to understand. A small metal ball, say for example some copper ball or whatever, metal ball is initially at 50 degrees Celsius or initially at 80 degrees Celsius, let's say, and it comes to 70 degrees Celsius in 8 minutes, let's say, for example, on an average. If you put it in air, let's say, in 8 minutes, then temperature of the body or temperature of ball, temperature of metal ball after 8 seconds, after 8 minutes is dash, after next 8 minutes is dash. Okay, so let's say for example if we try to solve this question, many times it happens that since in the first 8 minutes it is decreasing by 10 degrees Celsius, people feel that okay, this ball is decreasing 10 degrees Celsius for every 8 minutes. Okay, so then ultimately they are very tempted to write the answer 60 degrees Celsius, but actually it's wrong. Okay, so 60 degrees Celsius is not going to be the answer, because the reason is in the first 8 minutes the temperature of the body is changing from 80 to 70. Okay, but atmosphere is at some fixed temperature, let's say 20. Okay, so let T ambient, T infinity is equal to surrounding temperature is say some 30 degrees Celsius. Okay, so 30 degrees Celsius. Then what people feel is normally they'll feel in general they think this like an aptitude question. Okay, they'll tell you that in the first 8 minutes, if it's decreasing by 10 degrees, then the next 8 minutes also it decreases by 10 degrees. Okay, but this will never happen. The reason is, in the initial 8 minutes, the temperature of the body is high, and the difference between the temperature of the body and the surroundings is high actually. Okay, so more amount of heat gets lost. Okay, but in the next 8 minutes, what happens? The temperature of the body has decreased, and the difference between the temperature of the body and the atmosphere temperature got reduced actually. Okay, so in the next 8 minutes, means basically in the second 8 minutes, what happened? The temperature difference between the body and the surroundings got decreased, so that the amount of heat which flows out of the body decreases. Okay, so when heat flowing out of the body is decreasing, the temperature drop will become slow, and the temperature after this next 8 seconds would be definitely more than 60. Got it? Did you all understand the physics, what's happening here? Just I'm telling a bit of interesting stuff, that's it. Okay, why the answer would be definitely more than 60? Is this clear to all of you? Because what are the heat transfer that's happening in the first 8 minutes will not happen in the next 8 minutes, because the temperature difference between the body and the surroundings got decreased. Yes? Is this clear to all of you? Everyone, please type it in the chat box. Okay, so let's see if this is clear. Then let's solve. Solution. We have, you can say dt by dt is equal to minus k times of t minus t infinity. Okay, and t infinity is 30 degrees Celsius we have. So let's solve this. It is less than 60. Sorry, it is greater than 60. That's what I'm telling. Okay, the temperature will be in the next 8 minutes. Means finally, if you calculate that answer would be definitely more than 60. Okay, so let's check it up. Because the physics is, if the first 8 minutes temperature drop is 10, then the temperature drop in the next 8 minutes would be less than 10. Okay, if the temperature drop is less than 10, the final temperature would be more than 60 actually. Okay, so let's check. You'll get the same answer, something more than 60. So let's check it up. It's a differential equation that you have. So this value can be written as 1 by t minus t infinity dt is equal to minus k times dt actually here. Okay, so minus k times dt. So let's integrate this. So if you integrate this, you have ln t minus t infinity is equal to, because it's a logarithmic function, integration of 1 by this function is ln t minus t infinity is equal to minus kt plus constant, or you can also write this as t is equal to t infinity plus some constant into e power minus kt. Both are same. Okay, because initially if you take log to this side, it becomes e power minus kt plus c, so which can be written as c into e power minus kt. Okay, then t infinity goes to the right hand side. This is the variation of temperature with time actually. Okay, then let's see. Here there are two things to calculate. T infinity is known to you, but to calculate t at any given time, you should also know what is this k. Okay, proportionality constant is not given. So that's why I have given you a small metal ball is initially at 80 degrees Celsius. So it tells you, I've given some initial condition. So let's solve this. At t is equal to 0 minutes, whatever seconds. Okay, because I have mentioned in minutes. So 0 seconds is same as 0 minutes, of course, because the time has just started. So if t is at t equal to 0 minutes, temperature of the body is 80 degrees Celsius. Okay, so that's what you understood. So t is equal to 80 degrees Celsius. So let's substitute that in this equation. If we substitute this in this equation, this tells you 80 is equal to t infinity. So t infinity is 30 plus this constant times, if you put t equal to 0, this is e power 0, 1. So e power minus k times of 0 actually here. Okay, so e power minus k times of 0. So this value is 1. So ultimately c is equal to 50. C is equal to 50 actually here. Okay, so c is 50. So you got c. What about this value k? Let us do that. So therefore, the temperature function is t infinity plus this constant 50 into e power minus kt. This is the function. Now I have given you one more condition. The body is initially at 80 and it comes to 70 in 8 minutes. Okay, so if you start from t equal to 0 minutes, at t is equal to 8 minutes. At t is equal to 8 minutes. Okay, so at t equal to 8 minutes, the temperature of the body has come up to 70 degrees Celsius. Okay, so this has come up to 70 degrees Celsius. So if you replace this here, 70 is equal to t infinity is 30 plus 50 into e power minus k times of 8 is what I can write. Okay, so e power minus k times of 8. So let us compute this value. This is 30, 70 minus 30, 40, 40 by 50, so 4 by 5 is equal to e power minus k into 8, e power minus 8k. Okay, so this is e power minus 8k. So you can check this k value. If you simplify, k should be equal to ln 4 by 5 minus 1 by 8 times ln 4 by 5 is the value, correct? Because from this equation ln 4 by 5 is equal to minus 8k, so k equal to minus 1 by 8 times of ln 4 by 5 actually. And if you also check conceptually, I've told you this k should be always positive. If you are writing this minus sign here, this k should come positive, correct? Let's compute that value. We know that k is positive or negative. Ln 4 by 5, so 4 by 5 ln, okay, this value into minus 1 by 8 into minus 1 by 8 actually, okay, so into minus 1 by 8, 0.029 let's say, okay, so 0.027 or 0.028 you take, okay, so 0.028 actually. So this tells you k equal to 0.028. So clearly k became positive, okay, and we anticipated that k becomes positive because we have already taken the minus sign here, okay. That's what in the physics I've told you. If this k is positive, then there is a minus sign in this case, okay. That's we finally figured out. Then let's see in the next 8 minutes. So this differential equation is with respect to the time t and temperature capital T, of course. So in the first 8 minutes, this is the story what you have observed, okay. The temperature of the body came from 80 to 70. In the next 8 minutes, what would be the final temperature of the body? If I am telling next 8 minutes, then from the starting point, what is the time I should measure? Means in this question, basically if I start measuring time from the initial 80 degrees Celsius, what is the time at which I am interested in finding the temperature? What is the time that I am interested in finding this temperature? If initially it is 80 at t equal to 0, and if I am asking you in the next 8 minutes, then from beginning, what is the time that I am interested in? Come on, all of you. Kavan, Rambabu, Dev Singh, Saurabh, Shubham, Sheikh, Ahmad, Vijay. Can read only these names. So let's see. You know at time t equal to 0. Let's see. If you plot this graph, okay. This is t. This is t infinity. So initially the body is at 80. So after a long time, ultimately this body comes to in exponential to this. Basically it becomes asymptotic to this graph, okay. So this is time t, of course, in minutes, whatever, and this is t in degrees Celsius, okay. So finally at some large time, what happens? At some large time, this time becomes very large and e power minus infinity becomes 0 and t equal to t infinity. That's what you know, correct? Observe carefully. But see, the main problem is solving this differential equation, okay. That's it, but I'm trying to connect a bit of physics, that's all. So at large time, what happens? This term becomes large. So e power minus infinity becomes 0. So this is 0 and t will be equal to t infinity at some large time. Obviously, you know, if you keep any body of higher temperature on the surroundings, after sufficient heat loss, after some time, what happens? The body comes in equilibrium with the surroundings. Yes or no? So which means the final temperature of the body will be same as the atmospheric temperature. That's what this equation mathematically tells you. Correct? If t is tending to very large value, this value is going to be 0, then t is going to be t infinity. That's it. But now in this, we observed that the temperature at 8 minutes is 70, let's say, okay. Maybe this is not up to scale, very bad artist, okay. So this is 8 minutes, so this is 70, let's say, okay. Then they are asking you in the next 8 minutes, means this is something like this, it is 16. So what is the temperature, okay. Now you want the temperature at time t equal to 16, correct? So at t is equal to 16 minutes, what is the time t? Sorry, what is the temperature t of the body actually? That's what they want. Fine. Is this clear to all of you? Did you all understand this? Yes or no? Please type it in the chat box. Is this fine? Did you understand from this graph what I'm interested to talk about. So it tells you in the first 8 minutes you have observed a drop of 10 degrees Celsius. So the temperature has become 70 in the first 8 minutes. So in the next 8 minutes means total when the time is 16 minutes, what is the temperature of the body? That's what. Okay. So let's do. So since T is equal to, so T is equal to T infinity, which is like 30, or let's first write the things. T infinity plus C into e power minus kt. So this value tells like T is equal to, at T is equal to 16 minutes is equal to T infinity. So T infinity is 30. So this is 30 plus constant value C 50. We identified C is 50. Okay, so C value is 50 actually here. Then exponential of minus kt. Okay, so minus k value 0.028. Or you can replace, okay fine, you can just put that value minus 1 by 8 ln 4 by 5 whatever you have. So minus kt, so minus k minus 1 by 8 ln 4 by 5 into t, of course. Okay, so this is 16. So this is the value that you get. So let's simplify. This minus of minus gives you plus, then 8 cancel this 16 twice, of course. Then we have t at t is equal to 16 minutes is going to be 30 plus 3 times of exponential 2 into ln 4 by 5. So that can be taken on to the top. So ln 16 by 25. That's it. Okay, because it's like 2 into ln 4 by 5. So 2 into ln 4 by 5. This 2 can be taken on to the top of 4 by 5. So which is 16 by 25 actually. So let's compute this value. So t at t equal to 16 minutes. Definitely the answer would be more than 60. So let's check how much it's going to be. So let's compute the value. 16 by 25 ln. Okay, so e power ln 16 by 25 is 16 by 25. You know, this value is 16 by 25, of course, because it's e power ln. Okay, so I think then you don't need a calculator. Maybe 30 plus 50 into 16 by 25 actually. Okay, then you can figure it up. This is 2. So 30 plus 32, 62 degrees Celsius. Okay, the answer is more than 60. As you can see, there's only a drop of 8 degrees Celsius in the next 8 minutes. Okay, it is 62 directly because of this calculation. You see, we did not even I mean here just to calculate this value we have used calculator, but in fact this value need not be calculated. Okay, if you directly use this, then the answer is pretty simple, 62. Okay, so this is 62 degrees Celsius. Got it? Did you all understand? But in general, for the purpose of this class, once you have the differential equation, it's a first order differential equation which you have solved it. Okay, and it's a ODE, of course, ordinary differential equation. Yeah, okay. Fine. Is this understandable to all of you or not? Please type it in the chat box. If you have any issue, any concern, please talk to me. ये मैथ में आ सकते हैं क्या? एक बार दिया था. One time they have given this basically in, not this in the sense exactly this, some example like this, similar they're given. Then let's see. But of course it's a simple question. Okay, nothing much complicated about this. So the second application, maybe you can have so many applications, but now can someone tell me, this is for cooling, this is for cooling. If this is for heating, then K would be positive or negative? K would be positive or negative? Or if K is positive, this minus sign would be there or not there if it's heating? Heating, so heat is coming. Okay, so with time, temperature of the body is increasing. So this minus sign would be there or not there? Such case, this minus would be there or not there if it's heating. Okay, if the body is getting heated up, then with time, with increase in time, temperature is also increasing. Then will there be this minus sign? Will you have that minus sign? Then K is negative for the same configuration. Okay, or else you can keep K positive and delete this minus sign. You can do anything. Okay, that can also be done. Hello, let's look at the second one, radioactive decay or growth actually. Okay, normally these are called the population models general. Okay, so this is the population model, of course. Clear? So let's see radioactive, decay or growth basically. So let's see for any radioactive substance or bacteria sometime. Okay, so for any radioactive substance or the same, basically it's also called as population growth or decay model. Population growth or decay model. Okay, so you can use this name as well. So population growth or decay model actually in this case. Then for any radioactive substance, the current population of the substance, the current means, like let's say if you talk in terms of nuclei or in the name of bacteria cells, whatever, the current population of the substance is proportional to growth or decay in general. Okay, so like let's see if you have dn by dt. Okay, so if n is the current population, then dn by dt gives you the rate. So this is proportional to n, this is for growth. If they do not give you any model, then you can use this directly, and dn by dt is proportional to minus n for decay. Okay, here on the right hand side I have given you very simple functions because these are the general functions which are taken. Okay, if nothing is mentioned, but in the question if they have given you some complicated function, okay, on the right hand side they can complicate the functions if they want, but at the same time it will be a first order equation. Okay, always clear. So like example, this equation for growth tells you dn by dt is equal to kn, and it can, this n can be brought here, dt can be, like in the case of the previous one, we can also do this. K is positive in both the cases. So this also gives you the first order differential equations. Okay, yeah, so fine. Is this clear to all of you? So similarly in circuits, electric circuits, you'll get the, if you apply Kirchhoff's law and all, you'll get first order equations. So basically you can see in simple electric circuits, so let's say if you have a simple cell like this in which you have the resistor and you have closed it. Okay, so this is for example. Okay, so you have a capacitor maybe. Okay, then L into IC, inductance, all these things. If you have an inductor, capacitor, all these things. So in this case, let's say if there is this resistance R. Okay, then when you go along the circuit and if you apply the Kirchhoff's law, it tells you if this potential is V, for example, so V minus the potential drop across this is I into R is equal to 0, of course, and this V can be a function of time. I can be changing with time because if you keep changing the resistor. Okay, so let's say for example if resistance of this, because the things gets heated up, so this resistance need not be constant always. Okay, because with temperature resistance gets affected. So in general when modeling these functions you will end up with these equations. Okay, so V is equal to IR is basically the Ohm's law, of course, in this case, because there is no other thing. So in such case this V can be a function of time or it can be function of charge. Actually you can write anything, and if you write this I as dq by dt, and if you for example maintain R constant, then it also gives you a differential equation in all these cases. Okay, so anyway basically there are plenty of examples where you keep generating the first order differential equation, okay, in physical subjects at many places. So the idea is, the technique is to know how to solve this first order equation. That's the main idea. Clear to all of you? Yeah. So if these things are clear, let me give you one question to solve maybe. If for the equation di by dt, let's take one electric circuit equation, plus 0.2 times I is equal to, so 0.2 times I is equal to say 30, for example. Okay, so this is an equation. So it's some differential equation which you got, maybe 0.2 is the resistance, it can happen. Okay, so 0.2 is the equation. Then let's say they have given you some initial condition at t is equal to 0. At t equal to 0, the current in the circuit is, let's say, some 5 amperes, or not 5, maybe say 70 amperes. It's a high source, let's say, so it's a 70 amperes. Then the final steady state current in the circuit, then the final steady state, which means when that thing becomes steady after some long time as t tends to infinity. So once you solve this equation, put the boundary condition, you will get the constant. Okay, so once you get the constant, then arbitrary constant value, see, when you substitute this boundary condition, when you substitute the boundary condition, you can figure out what is the arbitrary constant value. Once you get the arbitrary constant value, you will get the particular solution. So in the particular solution, if you substitute t is equal to infinity, okay, then what would be the final value? Okay, that's called the final steady state value as t tends to infinity. Then the final steady state value of current in the circuit, I, is dash. Come on, solve this question. For this question, what's the answer? 62. Okay, so I think 2, but this poll is not working, I don't know today. You know, let's conduct, and I'll give you 150 seconds. It's a Leibniz linear equation, you can solve directly. The final steady state value, actually. Come on, quick, the time is rolling up. $100 amperes. I don't think it's 100, maybe some different value. So let's check it up. Okay, so anyway, you have tried. Look, I'll teach you 2 methods to solve this question. Actually, 150. Okay, maybe 150 could be the correct answer. Look, yeah, actually 150 is the correct answer. Let's check it up. I'll show you why. look. So if you solve this, given, let's write this word, given di by dt plus 0.2 I is equal to 30 actually. Okay, so I have confused you good enough. Actually this question can be solved in 3 ways. Look, I can give you that. The first method, which I would like to call, is di by dt is equal to 30 minus 0.2 times I actually. Okay, so then this tells you 1 by 30 minus 0.2 I is equal to dt actually. Okay, then if you integrate this, and you have di of course here, and this is dt. Okay, so if you integrate this, this value is 1 by minus 0.2 into ln 30 minus 0.2 times I is equal to integration of derivative is t actually here. Okay, so ultimately if you multiply this to the other side, ln 30 minus 0.2 I is equal to minus 0.2 times of time actually, because this minus 0.2, if it goes to the right hand side, it is t. Ultimately if you solve this, you will end up with something like this. Ln will go here, and 30 minus 0.2 I, I'm just putting a bit little careful here, so e power minus 0.2 t. Okay, e power minus 0.2 t actually, then I is equal to 1 by 0.2 times of 30 minus e power minus 0.2 t actually here. Okay, so this is the value which you get obviously. So I is equal to, and 1 by 0.2 is 5, this guy is 5, so I is equal to 150 minus, oh there should be some constant, right? Yeah, plus constant. Okay, so plus constant, so there should be some plus constant, so that can be written as a constant here, so a constant here also. Okay, so this case also the constant here. Let's see. This is what I would have got. Yes, please type it in the chat box. Is this what I would have got? Correct. 150 minus 5 times of constant is one more constant into e power minus 0.2 times t actually here. This is the solution. Even if you have solved it using Leibniz linear equation, you would have ended up with the same thing. Okay, now tell me one thing. I have given you some boundary condition at t equal to 0, I is equal to 70. Okay, so you will put t equal to 0 here, then I equal to 70, then c is equal to 80 is what you will get. Okay, so c value is 80, but after calculating this procedure and calculating the value of c, you got c is equal to 80. Good, you have done some calculation. But if you put t equal to infinity, what happens to this complete term? What happens to this complete term actually? Then after substituting the boundary condition and getting the value of c, then after that, since you want t is equal to minus t equal to infinity, if you put t equal to infinity, what happens to this complete second term? Come on, type it in the chat box. What happens to this complete second term actually? If you put t equal to infinity there, what happens to the complete second term? 0. So anyhow you will get c equal to finite value, but whatever the value of c, as long as you put t equal to infinity, this second term becomes 0. So there is no impact for that second term. Okay, so there is no impact of this calculation of c actually in such case. Okay, so therefore at t tends to infinity, this I will reach a steady state value of 150 amperes. Okay, that's what you know. Correct. I is equal to 150 amperes is what you get. So t is equal to, at t tends to infinity, I is equal to 150 amperes. This is one way of solving this. Okay, or the standard procedure which you have, di by dt plus 0.2 times I is equal to, how much did I give? 30. Okay, so this is 30. So ultimately this is Leibniz linear form. Leibniz linear form actually here. Then this tells you integrating factor is equal to e power integral 0.2 dt, so which is 0.2 t of course. Okay, so integrating factor is e power 0.2 t of course. Okay, then what is the solution? Solution is I is the dependent variable, so I into e power 0.2 times t is equal to integral 30 times integrating factor dt plus constant. Okay, so it tells you I into e power 0.2 t is equal to 30 is constant. Integration of e power 0.2 t is e power 0.2 t divided by 0.2, okay, plus some constant. This is what you get. Now 30 by 0.2. What is 30 by 0.2? 150. Okay. So I into e power 0.2 t is equal to 150 times e power 0.2 t plus constant. So ultimately, if you cancel this e power 0.2 t on both sides, you'll get minus e power 0.2 t on the right hand side, of course. Okay, by cancelling these two. So this tells you I of time is equal to 150 plus some constant into e power minus 0.2 times of t is what you're getting, correct? So this is a constant. So plus some constant into e power minus 0.2 t. Here did we get minus? How did we get minus actually? Some minus and we have missed. Okay, anyway, that's a arbitrary constant. So this c is just an arbitrary constant. So if you put value, both the values of c would be 80 actually, okay? Because here this is something like if you put t equal to 0, then I value would be plus 80 here. Here also we got this c value to be 80, I think, right? Yeah, whatever. It's just an arbitrary constant. So accordingly, if you substitute the boundary condition, the answer would this final solution would remain same. So again, this is the same solution. If you put t equal to minus, if you put t equal to infinity, this term becomes 0. So I is equal to 150 amperes. Okay, so you know we can say as therefore as t tends to infinity, ultimately again I is equal to 150 amperes. So this is also the solution, the same solution what you got basically by doing this here. Okay, so at t equal to infinity, this is 150 amperes, and the same here at t tends to infinity, I is equal to 150 amperes. These are the two ways, and if you do in any one of these two ways, you'll get the same answer. Okay, but I have actually played a little trick with you. I have made you to do either this or this, correct? All of you have done one of these two methods, yes or no? Come on, type it in the chat box. Yes, all of you have done one of these two methods actually. Yes or no? Yeah, and some of you might have spent time in calculating this arbitrary constant c value also. But of course, which even if you calculate c, that do not play much impactful role here. Okay, so let's see. Or let's do one more method. Di by dt plus 0.2i is equal to 330 is what you get. Okay, now okay, second method or first method, majority of you might have done one of these two methods. But let's see, in the question I have mentioned one thing, the steady state, final steady state value. Okay, so what do you mean by steady state? All of you might have done, you know, at least first 2 years of engineering or first year of engineering. What do you mean by steady state? Let's say if things are steady, then what do you mean by that? Is there any change with respect to time? I is depending only on time. Okay, there is no other variable which is dependent. Okay, I is depending only and only on time. So that's why we have it in the exact derivative di by dt. So if things do not change with time, then what should be the case? Means if things are steady, then things are not changing with time, which means after doing all this, I'm fine, Kem. Thank you for asking. You all understand? If it's steady state, then ultimately di by dt is going to be 0. So that means at that particular final state, if things are not changing with time, I value is going to be 150 amperes right away. Got it? Yeah. Did you all understand? Yeah, I understand. I know. Doing this will bring a lot of smiles on many faces. Correct? I know many of you felt happy after seeing this, but this is the way of understanding the physics. If someone would have given me this question, I would have done this. Okay, rather than doing all this stuff. Clear to all? That's what steady state. Okay, because actually in general, if things are at steady state, only the partial derivative with respect to time of anything would be 0. Okay, but in general this quantity depends on time, dimensions x, y, z, all these things, but here it's purely dependent on time. So we have written only di by dt. So that's why the di by dt term is 0, because it's steady state. So at that particular steady state, if this is 0, I value is 150. Yeah. So anyway, we'll wind up here because it's almost 8:30. The time has flown a bit faster today. It's okay, fine. So we'll, in today's class, we figured out conversion of non-linear equations, ODEs, of course, okay, of first order again, to linear ODEs of first order, which we have seen, and the second is applications, some nice applications we have seen in today, okay, of first order ODEs, okay, and then in tomorrow's class, at 7, of course. So we will talk about higher order differential equation, okay, higher order ODEs, ordinary differential equations, whatever. So again, in the syllabus we have only linear higher order differential equations, because to be frank, even if it's, you'll see in linear case there are slight issues which we will figure out in tomorrow's class. Okay, so these are the cases, higher order ordinary differential equation. Clear to all of you? So fine then, I hope all of you enjoyed the session. We'll meet tomorrow again at 7 p.m. okay, learn much more techniques, some nice insights of differential equations again, and thank you for, okay. Every now and then you'll get differential equations, you'll keep getting differential equations, okay. So this is really one of the most important module, and in fact more than this, PDEs are very important, but since PDEs are slightly one step above, in GATE examination the syllabus of PDEs was constrained so much, okay, but again doing PDEs is really helpful, okay, and 100 out of 100% of the times you'll get PDEs in solving the systems, okay, but we'll neglect so many things to make them ODEs. Yes, okay, so thank you all. We'll meet then tomorrow again at 7 p.m. and we'll start higher order differential equation, complementary function and particular integral concept. Yeah, of course, these are the things which we are going to look at today, I mean in the tomorrow's class, okay. So we'll first define what are the equations, then what are the class of equations we'll solve, then we'll see what is a homogeneous equation in higher order, and eventually we'll solve the. So fine then, thank you all. We'll meet tomorrow at 7 p.m. and we'll talk about the higher order equation, okay. Thank you, bye.